did this, Fn over Fn minus 1, and we let n get really big, where we do one Fibonacci number over the one before it, this approached a one particular value, 1.61803, right? He's going to do an exploration with the Lucas numbers that he showed you that has the same rule as Fibonacci, but it starts with 1 and 2. And if you look at the ratio of a Lucas number over the one before it, that is going to somehow relate to the Fibonacci ratios. And I'll let you do the exploration on your own. No, not right now. So we're going to talk a little bit about the Fibonacci numbers and the golden ratio in nature, art, and architecture. So some of this you saw mentioned in the video we just watched. But first, last class we talked about gnomons, and those were things that you glue on to a shape to make a new shape that's similar to the original. And I just thought I'd tell you where the word gnomon comes from. It's Greek for one who knows. And a carpenter's square, which looks like this thing, which is this, was called a gnomon because it knows how to make a right angle. And one possible gnomon to a rectangle is an L. It looks like a carpenter's square. So the word was applied to the geometric concept in general. So that's where gnomon comes from. And we talked about this very briefly at the end of the last class, where we said natural organisms grow in essentially two different ways. The first, like us, is all-around growth. All living parts of us grow simultaneously, and there's no obvious way to distinguish between older parts of ourselves and newer parts of ourselves. But then some other organisms grow where they have a new part added to the old part. And at any stage of the growth process, you can see exactly what the organism looked like in its past. And organisms that grow this way like to maintain self-similarity, so they maintain their shape even as they grow larger. And for an organism to maintain its shape as it grows, new growth has to be a gnomon of the entire organism. So that's why we studied gnomons. And the process is called mnemonic growth. And these are a few examples. Okay, so we have trees. They add rings as they get older. So you can tell exactly what that tree looked like in the past. Or the nautilus shell. It adds chambers as it grows older. So when this was a little tiny baby, it might have just been this part, and then it adds chambers as it gets older and older. So it has the same shape, but just keeps adding these chambers to get bigger. And then the sunflower, when it's little, it might have only had that. It just had these spirals that go like this. And then as it gets bigger, we continue the spirals out. And so we have it maintaining the same shape, but growing larger. And in both of the cases where we have the spirals, the spiral looks like this thing that we made last class that seems like a totally abstract spiral that we made using Fibonacci rectangles. So I started by making squares that had side lengths that were Fibonacci numbers, and each rectangle turned out to be a Fibonacci rectangle. Like this rectangle right here is 8 by 13. And each square has side length that's a Fibonacci number, 34, 34. So by building this Fibonacci-based thing, we create this spiral, and it is exactly the spiral that we see in nature. So it doesn't spiral, no. No, it's just rings. Yeah. So they're both mnemonic growth in that, so this one started out as a circle, and if it's going to grow bigger and maintain its shape, it has to add rings, right? It's just adding rings. So this isn't a spiral. The gnomons that are being added are just rings.
Now, is that still considered a Fibonacci?
Nope, this one doesn't have as much to do with Fibonacci. Yeah, but it is mnemonic growth. Okay. And this one is mnemonic growth too, but it grows in this spiral fashion. So the video we just watched had an explanation for the spiral growth that we see in nature. And I'm just going to go back to that and see if I can illuminate it a little more. So he started to explain it, but I thought he was a little vague. So I did a little more research to try to figure out why we get these spirals. So it has to do with packings, the most efficient way to pack things in a given space. So the best way to pack square objects is to stack them like this, right? If you just had boxes, you just stack them and make a perfect grid like that. And the best way to pack circular objects is in a hexagonal arrangement like this, right? So like if you were stacking logs or wine bottles or something, you know, you'd kind of like rest one in between the two below it. So you might think that seeds are round, you might expect a hexagonal packing like this. But seeds don't have consistent size, right? If I'm talking about the seeds like on the head of a sunflower. They don't have consistent size. They're small at first and they grow larger as time passes. Also, they have to fit in a circle, right? As opposed to this thing, which is, you know, vaguely rectangular, right? So I have these seeds that they need to fit on a circle, and I want them to be able to grow larger as time goes on. So I'm looking for a packing that will fit as many seeds as possible in a round area without overcrowding any one spot, and that will maintain this efficiency even as the seeds grow in size. So this is like a really difficult problem. If I asked you to do this, it would be really difficult. So it turns out nature uses an angle of about 222.5 degrees, or equivalently 137.5 degrees, depending on which direction you go, right? You're going to end up in the same place. And that's how it decides where to put the next seed or leaf or petal on the plant. So this is Vi Hart. I showed you last class, this video. It's posted in Moodle for you if you want to see it again. And she explains how this works. Oh, actually, I think this might be a different video than that. So why did Fibonacci numbers pop up so much in this trying to create the most efficient packing possible while letting the seeds grow and filling a circular area? Well, remember the ratio of successive Fibonacci numbers is the best approximation you can get for phi using a ratio of two whole numbers. Because phi is irrational. So if you're going to take two whole numbers, you can never write phi as a ratio of two whole numbers. That's what it means to be irrational. But the best we can do is to take a ratio of two Fibonacci numbers. So plants attempt to use phi as their guide to growth, but a plant can only have a whole number of petals or leaves or seed spirals. So it ends up with numbers that are Fibonacci numbers in its attempt to use phi to guide its growth. So the golden ratio and Fibonacci numbers show up a lot in nature. And just really, next time you go to the supermarket, look for anything spirally and count the spirals, and you'll see the Fibonacci numbers. But they also pop up frequently in art and architecture, and there's something that seems to be aesthetically pleasing about it to us. And maybe it's because it reflects nature. Sometimes there's evidence that the artist or architect invoked the ratio on purpose, and other times it seems coincidental, like it just seemed pleasing or right. So the Parthenon of ancient Greece shows the golden ratio all over the place. Okay, so if you look at this rectangle, actually I think maybe it includes the roof. I think it includes the roof. Go up like that. This rectangle. If you do length divided by width, you get the golden ratio. Same with all of these little rectangles along the top and these rectangles. and there are 8 columns along the front and 13 columns going back. So this seems pretty premeditated to have used the golden ratio here. And we see it in tons and tons of places. We can superimpose the golden spiral made from Fibonacci rectangles on top of it, and it fits perfectly. So another artist that seems to have used it on purpose is Leonardo Da Vinci, and you can see golden rectangles superimposed over all of lots of his work. I think Leonardo da Vinci was also a bit of an amateur mathematician, and I believe he wrote about it, yeah, using the ratio. Particularly in this piece, the Vitruvian Man, all these rectangles are golden rectangles. And so these are all marked. All the rectangles you see in here are marked as golden rectangles. And in our first class about Fibonacci and golden ratios, we talked about the golden triangle, which was a 36, 72, 72 triangle. And there seem to be 2 of those superimposed on this painting. 36, 72, and 72. Because one of these longer sides divided by the shorter side is the golden ratio in that kind of triangle. The Egyptian pyramids show the golden ratio. If you take this thing, which is called the slant height, we'll call it S, and divide by this distance from the center out, I don't know what we should call this, C, okay. S divided by C is approximately the golden ratio in the ancient pyramids of Egypt. Don't know if that one was on purpose. The Cathedral of Notre Dame, I believe, was one that's done on purpose. There are lots and lots of rectangles that all show the golden ratio. They're all golden rectangles. And you can't see it in the notes that I handed out, but anytime you have a white segment divided by a blue segment, you get the golden ratio. And also, the whole segment divided by the white segment gives the golden ratio. We see it in today, still, modern art and architecture. This, I believe, is the UN building, and these rectangles are golden rectangles. This is a Georgian-style house, all kinds of golden rectangles in there. No, I'm not. That's it. Right. Mm-hmm. So we have some other art pieces here. This is a stained glass window that has several golden rectangles in it. And often artists don't put the subject of their painting right in the center. Sometimes they use a rule of thumb called the rule of thirds, right, where you might break your paper into thirds like this and put the subject about right here, right, or in one of the quadrants. And the rule of thirds, let me erase everything I've got here. By doing that, you end up using something of an approximation to the golden ratio, where this length divided by this length, call this L2 and L1, approximates the golden ratio. Okay. Yep, vertically also. So it approximates the golden ratio, and it's just, We use a rule of thirds because you're out in the field and you're trying to approximate where you want to put something, and you can't be measuring the exact thing of a golden ratio. So we use the rule of thirds and we say that's close enough. So this is something that I've had students do as projects is try to create a piece of art based around the golden ratio or a golden spiral or something like that. So, or you could build something like this if you're good at carpentry type things. So this is a factory made versus a carpenter made by a carpenter by hand using the golden ratio in designing the height of the drawers. And I don't know, is this one nicer, the golden ratio one?
It's bigger. I'd buy that one over.
You would?
Because the drawer space,
better drawer space, yeah. More efficient use of space because you put big things down here and smaller things up here. Yep. And the golden ratio pops up in poetry and music and film and lots more in nature that we haven't discussed. So an in-depth discussion of nature's or humans' use of the golden ratio might make a great project, right? It definitely happens in music, and I know nothing about music, so that could be a cool project. That's why I didn't do anything about music in our class discussion. So if somebody's into that.
Google the golden ratio in music.
Oh yeah, you get tons of stuff.
Really?
Yeah.
Got, like,
yeah. So yeah, that could be a really cool project. Somebody could write a song that uses the golden ratio, or you could analyze a song that uses the golden ratio, something like that. And although the human body exhibits overall growth as opposed to mnemonic growth, we still have the golden ratio in us. There are tons and tons of measurements where if you take the ratio of one measurement to another measurement, you get approximately the golden ratio. In each individual person, it might not come out to exactly the golden ratio, but if you take an average of all people, you get pretty close to the golden ratio. So if you do, let's see, what's a good one? The end of your calf muscle, right? So like down here to your ankle, and then the calf muscle to the sole of your foot. Golden ratio.
So if you like lie down on a big piece of paper
and mark it, yeah. Well, that's an interesting question, yeah, because part of why, you know, as kids grow, they get really like gangly and awkward looking, and that's partly because this ratio gets thrown off as you're growing. Some things grow faster than others. Right, yeah. Yeah, but exploring these ratios could be an interesting project also, for sure. Yep. Okay, so I'm going to give you the rest of class, which is 10 minutes or so, to work on this homework assignment. It's a worksheet to help sort of pull together all the things we've talked about with Fibonacci and golden ratio.